All right, before I start with the new stuff, anybody have any questions about homework or the test? I forgot to give homework yesterday, so.
Number 1C.
On the test?
Yes.
I don't have it with me. Do you remember what?
You were asking us what the, and I don't know which the wording was either the length or the delta?
Oh, yeah. Okay, yes. All right. Well, so the idea of that, and that's going to be worth 1 point out of the 6, so it's not like a big points issue, but the idea is that the Poisson's effect, that affects every dimension that's not the axially loaded dimension. So if you have a member like this, and you apply forces like this, it stretches, right? Yeah. The face that's facing us here, the length gets smaller. That pitches.
Yeah.
And the same thing happens with this, and they both happen according to Poisson's ratio.
Yep.
So let me just make up some values here. So if you have okay, so let's say that this starts out as 0.1, and this starts out as 0.02, and this starts out as 0.03. Yeah. And after the deformation, these lengths become, so you stretch it and you get that this length is equal to 0.1. Okay, these are not going to be realistic numbers, but let me just put some numbers on it. 0.101. And this distance is going to be, so what's that? 1, 2. That's 1/1000th. So this would have to be like 0.0199 1, 2, 3. I think, is that enough nines? Let's try it. I might have needed one more. And then this dimension is going to be something. Okay. So Poisson's ratio says that if this is the x-axis, that loaded axis, and this is the y-axis, and then the z-axis would be going this way. Poisson's ratio says negative strain yy over strain xx is equal to negative of the strain zz divided by strain xx. And so we just have to calculate these values. Strain xx is equal to 0.101 minus 0.1 divided by 0.1. And so that is, I think that's 0.01 if you do that. Something like that. That's a really big strain. We're not going to deal with strains like that really in actual calculations, but or if we do, our results are not going to be very accurate. They're going to be drastically inaccurate, in fact. They're going to be worthless. Strain YY is equal to 0.0199 minus 0.02 divided by 0.02. What do you get for that one? It's going to be negative because it's getting smaller. 0.0001 divided by 0.02. Okay, negative 5 times 10 to the minus third. And so these things together tell us that Poisson's ratio is equal to negative of negative 5 times 10 to the minus third divided by 0.01. And I think you just get a value of 0.5, which is the biggest Poisson's ratio can be. That means that in any deformation, the volume doesn't change. Okay, so now we're going to use it with, so now we're going to use this. So the ZZ strain is equal to this unknown length L minus 0.03 divided by 0.03. And Poisson's ratio is 0.5, and that's equal to negative of the ZZ strain divided by the XX strain. And so that says, you could rewrite that as 0.03 minus L is equal to 3 times 10 to the minus 4, I think. I mean, over 3 times 10 to the minus 4. So 1.5 times 10 to the minus 4 is equal to 0.03 minus L. And so what do you get there for, so for L you'll get 0.03 minus 1.5 times 10 to the minus 4th. So I guess that's 0.02 085. Huh? Yeah, 9. Okay, so that was the idea of that one. It just took recognizing that Poisson's ratio applies in the z direction just like it does in the y direction. So you can use the values we have to calculate Poisson's ratio and then use Poisson's ratio to figure out the deformation in the z direction.
Were you looking for that deformation length or the change in, I don't remember. I didn't remember how you worked it.
I don't either. But then if you wanted the change, it would be, well, it would be this. That would be the delta. Any other questions about that? Any other questions about the test or homework? Yep.
Does homework due at the beginning of class on Wednesday?
I don't care about that. You can turn it in whenever. You could turn it in. Thursday would be better, really, because then you can use it to study. So let's say it's still okay to turn it in Wednesday, but you should turn it in Thursday. Okay. Any other questions? So now, what kind of loading situations are we able right now to calculate stresses for? So we talked about what stress is, the relationship between stress and strain, all that stuff. But we're just starting to be able to calculate stresses in actual bodies. So what's the one situation that we've dealt with so far? Axial is a subcategory of, so if anytime we happen to have a body that's loaded according to the rules of stress elements, we can calculate the stress. And axial loads are in that category. So now we're going to talk about stresses in beams. This is trickier. The other one is fairly easy. What is a beam? Anyone know? I think this might have come up in statics. So it's funny, a beam, the definition of a beam doesn't just depend on what the object is. It also depends on how it's loaded. So a beam is a long, slender body that's undergoing non-axial loading. It can also be undergoing axial loading, but there has to be some part of the load that's acting non-axially. So you can have axial loading, that's allowed, but there has to be something else going on. Shoot. And like, for example, this is something you're used to seeing being used as a beam. Okay, and the reason that's used as a beam is because so this shape is used for beams. Because it's good at resisting deformation. When non-axial loads are applied. Okay, so say that this is, so if you look at the cross-sectional area of this, let's say that it has some certain amount of, it has some certain amount of cross-sectional area. You could arrange that amount of area in a lot of different cross-sectional shapes. You could do a circular tube that had that same cross-sectional area. You could do a rectangular shape. Infinitely many cross-sectional shapes you could have that same cross-sectional area. And if you took all those different cross-sections of beams and applied axial loads, like put it into tension or compression, they'd all be the same at resisting stretching or compression. But if you applied a load like this and a load like this, not along the long axis of the beam, you'd see that that equivalent cross-sectional area where the cross-sectional shape is a circle, it would have a lot more deformation due to the bending happening here than an I-beam would. And that's what an I-beam is good for. Okay, so that's why you use shapes like this in beam applications, as opposed to just, obviously it'd be simpler to make just a rectangular shape or a circular cylinder or something. Okay, so we're going to deal with beams loaded in the following ways. So stresses. Yeah.
Are you saying this one is stronger than if it would be a pentagon, something like that?
Yeah, so, right, this is stronger in beam applications than a rectangular shape using the same amount of material or a circular shape using the same amount of material.
How about like rectangular tubing?
Yeah, that has a lot of the same advantages. What this has going for it, and we'll talk about this mathematically, but what this has going for it is a lot of the material is spread far away from the center line, from the centroid, and so rectangular tubing has that same thing going for it. Okay, so stresses in beams come from 4 types of internal loads. Tension or compression, the shear force, the bending moment, and the torsion. And because all of the applications that we're capable of looking at require small deformations and a linear relationship between stress and strain, for our applications, we sort of luck out in this way. We can calculate the stress due to these internal loads individually. So do 4 independent calculations of stress, and then just add them together to get the total state of stress. So we can calculate the stress due to each of the 4 internal loads. Independently. And then add up the stress tensors to get the total stress tensor. That is called the Superposition Principle. That's a great name. Superposition. And it's a really useful thing whenever it comes up. It just says that you can take a complicated situation, break it up into a bunch of different causes, calculate the effect due to each one of those causes, and then add them up to get the total. And you use it in electrical engineering a lot, right? When you do that. Okay. Right. So this is a useful thing whenever it comes up in a lot of different areas of engineering, and we're going to take advantage of it here. All right, so before we can calculate those stresses, we have to know how to calculate those internal loads. We need to be able to calculate the internal loads. So that's what we're going to do first. Figure out how to calculate internal loads in beams. Okay, and so I'm going to start with just the most basic idea of what internal loads are, and then we'll go from there. So here's an example. Let's say we have a cantilever beam connected to the wall at the left end. And let's say that we have a force of 1,000 newtons that's acting at a 45-degree angle from horizontal. And then let's say we have a couple applied about the axis of this beam with a value of 5,000 newton meters. We'll say the whole beam is 1 meter long, and we want to calculate the internal loads at the midpoint. Okay, so first, this notation for this couple. That double arrow notation means, a couple is always two equal and opposite forces acting at a distance from each other. So if that's a body and you have a force this way and a force this way, those produce a moment. In this case, it would be, bless you, in this case, that moment would be counterclockwise, right? And so according to the right-hand rule, what's the direction of that moment? It's in the, so it's right, that's right that it's a counterclockwise moment, but the right-hand rule says that as a vector, that moment would be pointing out of the page. Okay, so that moment would only have a component in this direction. So I'll write it as a circle with a dot that's like an arrow coming out towards us, and that moment m is equal to f times the distance between them. If instead you have a force acting this way and a force acting this way, producing the couple, that has the effect of twisting this beam around its axis, okay? And the direction of the moment that it would produce is like this. And so as a vector, that moment is to the right of the page. And so you would write this as a moment with a double arrow pointing to the right. Okay, so when I say, like in this picture, that 5,000 Newton meter moment pointing to the right, it means that there's a torque being applied to the end of this member that's tending to twist it like this. Okay. Okay, so we're going to make a cut. This beam, we're going to isolate the half of this beam that ends at that dotted line. We could do it from either direction. And then the internal loads that we're going to calculate are the loads that are applied to our chosen part of the beam by the connecting part of the beam that we're not considering in our free body. So we're going to, I'm getting ahead of myself. We first need to calculate the external loads at the wall. Okay. So first, calculate the reactions at the wall. Okay, so free body diagram of this beam. We have all of these applied loads, the 1,000 over here, the couple of 5,000 Newton meters, and then the fixed joint at the wall. What kind of loads can a fixed joint apply to a body? Yep, so full force vector. In this case, everything's just happening in this plane, so I'm just going to do a plane vector. I'll call it R. And then there's up to a full vector of couples. I'm going to write it as a component of a couple about the z direction. And this fixed joint also keeps this torque from making this spin around its axis. So in order to do that, it has to, the wall has to apply a reaction torque to this side to keep it from rotating. Okay, so I'll put it in here like this, and I'll call it torque sub R. Okay, so Newton's second law says we're going to add up the force. What? Yeah, we're going to. You're right that it's going to end up being in the opposite direction, but I just always draw it in the positive axis direction and then let the signs work out on its own. Okay, so Newton's second law. So we're just dealing with the forces first. We have that force vector R. Yep.
So your RY would be your shear force, your RX would be your tension, the M is your bending moment, and then the IR is your torsion?
Well, actually, no. Right now we're calculating just external loads. So it's going to be internal loads once we, so right now we're isolating the whole beam. But after we're done with this, we're going to isolate half of the beam. And we're going to calculate the loads applied to the half that we're isolating by the adjacent parts of the beam, and that's going to be the internal load. But they are related to the, that's in the same ballpark as what you're talking about. We're going to end up calculating a horizontal force component that's equal to the tension, a vertical force component equal to the shear force, and yeah.
But if you have the moment arm, why you need the torque?
If you have what?
The moment is, we have the moment, right? They are going to perform rotating. Why we need a torque?
Why do we need this? If you apply, so there's two kinds of moments going on. There's this force is applying a moment that's trying to bend, it's trying to rotate it this way. And then this torque is trying to make it spin about its axis. Okay, and we need components of couples at the wall to prevent both of those two types of motion. Any other questions about that? So in statics, the new thing that we didn't do in statics is we didn't use this axial torque, right? That's a new one. Okay, so Newton's second law says the r vector plus this, if you write this in vector components, is negative 707.1, negative 707.1.
Where's that coming from?
That's this.
Okay, yep, okay.
And everything else up there is a couple. It's a moment, so it's not going to appear in Newton's second law. So this r vector, just solve for it, and you get positive 707.1, positive 707.1. And now I'm going to break up the moment equation into a z equation and an x equation. We're most used to using the z equation, so I'm going to do that first. So the rotational Newton's second law about the z-axis. And we can choose whatever we want as the about point. I'll choose the about point here at the left end. Okay, so what are the, okay, well, let's just go through these and think about whether each one of these loads produces a moment about the z-axis. So what about MR? Does that produce a moment about the z-axis? That's a couple. It's like a pure moment, and that, that, if you use the right-hand rule, that's in the z direction. It's producing a moment about the z-axis. So we just add that one on. What about torque sub r, T sub r? That's in the x direction, about the x-axis, so that doesn't produce a moment for this equation. What about r? It doesn't because it's acting at the about point. What about this 1,000? Yeah, well, we can think of breaking that up into components. We have a component here that's 707.1 and a component here that's 707.1. The horizontal component doesn't produce a moment about z because the line of action of that component goes right through the about point. What's the moment arm for this vertical 707? What did I say this length was? 1 meter. Okay. So yeah, the moment arm of this downward 707.1 is 1 meter. And would that produce a clockwise or counterclockwise rotation around this about point? Yeah, so if this had a hinge at the red dot and you took a little hammer and tapped the downward force on the end, and this was free to rotate, you get a rotation that way. Okay, so that would be a clockwise rotation, and so that's going to be a negative moment. So you have a moment arm of 1, a force magnitude of 707.1, and it's negative. And then the last load is the 5,000 Newton meter couple, that torque. Does that produce a moment about the z-axis? Nope, that's x-axis. So this is all equal to 0. And so that tells us that this MR is equal to positive 707.1 Newton meters. And now we'll do the rotational version of Newton's second law about the x-axis. And as an about point, let's think of like the center line of the beam extending all the way down the length of the beam. That's not going to come up because all the moments that are happening in the x direction are couples, so they don't depend on the about point. Okay, so let's go through it again. Which of these produce moments about the x-axis? TR? Yes? That's a couple, so we just add it in. MR? No. R? No. The 1,000? Well, we're treating that like it's acting, like it's being applied to the center of this beam, so no, that's not going to produce any moment about the center of the beam. And then the last one is the 5,000. Yes. That's a torque about the x-axis. Is it positive or negative? Positive because it's in the positive x direction. So positive 5,000 plus 5,000 is equal to 0. And so the reaction torque is equal to negative 5,000 Newton meters. Any questions about that part? That's the external loads. So we haven't started the internal loads yet. So now we're going to isolate the left half of the beam. And we're not going to isolate the right half of the beam because Newton's second law and the rotational equation only give us information about external loads. Okay? So if we're going to calculate forces that are applied to the left half of the beam at that red dotted line, we need to make that red dotted line the boundary between what we're isolating and the rest of the world. That's the only way you can ever use Newton's laws to calculate loads. Okay? Those loads have to appear on the boundary of what you're isolating. Okay, so we're going to isolate the left half of the beam, and we're going to calculate the loads applied to the left half by the right half. So I'll draw the part we're isolating in black, and then I'll put the rest of it in blue just to show where the part is that we're leaving out. And we're going to think about what loads are applied to this black piece that we're isolating. Okay, so all of these are acting on the piece that we're isolating now. And we've calculated the values of these. So TR is equal to negative 5,000, or else you can just draw the arrow in the other direction and write it as positive 5,000. MR is 707.1. That's like this. Then we have this force vector that's equal to 707.1, 707.1. What about the loads at the right end of the beam? Do those appear in our free body diagram? Nope, those are acting on this part that we're not considering. So there's this torque over here that we're not worried about, and there's this force of 1,000 we're not worried about. But in order for this to be a complete free body diagram, we have to deal with all the contact forces all the way around the boundary of what we've isolated. And you can see that there's contact between the part we've isolated and this other part here, and we have to deal with that. And so the way to think about that is this contact point between the part we're choosing and the part that we're not choosing is a fixed joint. And so the types of loads that can be applied here by the stuff in blue are all the loads that a fixed joint can apply. So that is a full force vector. All right, that is R. And a couple about the z-axis. All right, that is M. And a torque about the x-axis. All right, that is T. And I'm always going to write these torques as like fancy T with the hat and shoes to differentiate between the regular T that is what we're going to use for tension. Okay. So now Newton's second law says 707.1, 707.1 plus Rx, Ry is equal to zeros. And so this gives us that reaction force vector is equal to negative 707, negative 707. And then we'll do the moment equation, rotational Newton's second law, about the z-axis. And as an about point, I'm going to choose the left end of the beam. Okay, so does the 5,000 apply a moment about the z-axis? Nope. The 707? Yes, so positive 707.1. The force? The force at the left end point?
No.
No, because it's acting at the about point. The moment M?
Yes.
Yes. The torque T?
No.
No. And then the y component of the force at the right end applies a moment. The x component doesn't apply a moment because its line of action goes right through the about point. So what's the moment arm for that y component of the force R?
0.5.
Yep, 0.5. So we have a moment arm of 0.5 times the force Ry, the y component of that force R. And then if you think of that force Ry causing a rotation around that red dot, would that force make it go clockwise or counterclockwise? Counterclockwise, so that's positive. This is equal to 0. So this says that M is equal to negative 707.1 minus 0.5 Ry. And we know what this Ry is. We just calculated it. So now we can substitute that in here. So M is equal to negative 707.1 minus 0.5 times negative 707.1. And we get that M is equal to negative 353.5. This is in Newton meters. The one for the force up here is in newtons. And so the last thing we have to do is use the x component of the moment equation to calculate that torque T, that internal torque T that's applied to the left half by the right half. And our about point, again, you can think of it as the center line, but it's going to be pretty common for the only moments applied about the x-axis to be couples, so you don't care about the about point anyways. Okay, so let's go through all these loads now, and we have to figure out which one of those apply moments about the x-axis. How about that 5,000? Yes? What's the sign?
Negative.
Negative this time. How about the 707.1?
No.
Nope. The force?
Yes.
Nope. That force we're talking about, so we're talking about a force that's applied here with those components, and we're trying to figure out if that would cause a torque around the long axis of the beam. It's applied, maybe the easiest way to think about it is that force is applied on the center line, which is our about point. So no. What else do we have? So now we're over to the ones on the right end. Does that force R apply a moment about the x-axis? No. The moment M? Nope. It applies a moment about the z-axis, not the x-axis. And then the torque T applies one about the x-axis. So this says that the torque T is equal to positive 5,000 Newton meters. So now we have a list of all the loads that are applied to the left half of the beam by the right half of the beam at the midpoint of the beam. There's a force here, there's a moment, and there's a torque. Yep.
How come the Rx isn't found?
Because the x component is, if you draw the line of action of that x component, it goes right through the about point. And by the way, for all of these, if anybody wants to write out that table to solve it, you can do that. Usually, I think for most people, once you get used to doing it this way, it's faster for this kind of problem. And it doesn't, there's no real downside to doing it this way. Okay, so those are the internal loads that are applied to the left half by the right half. There are two more things that we have to think about here. The first one is that what would happen if we had isolated the right half and calculated the loads applied to the right half by the left half? So if we had isolated the right half instead, yep, they'd be equal and opposite. It's a Newton's third law thing. You're talking about the loads applied to the left by the right versus the loads applied to the right by the left. So they'd be equal and opposite. And the problem is we'd like a sign convention where those internal loads represent the place on the beam that we're looking at and not how we calculate it. Okay? So we'd like to get the same internal load values at that point, or at a point, independent of how we calculate it. Okay, so that's going to introduce a whole new sign convention that seems a little, it seems totally arbitrary when you see it, but the reason that we don't keep the vector sign conventions that we're used to is so that we have this independence of how we do the calculation. You don't have the equal and opposite issue coming up. And then the second issue is we'd like to be able to calculate these internal loads at every point along the beam. We've done 1 point along the beam, so how many do we have left?
Infinite.
Yeah, right, and uncountably infinite, so that's not good. So it doesn't seem like this is really the way to go. So you could just start calculating internal loads at points, but, you'd never get there. So the next thing we want to do is we want to represent these internal loads as functions of x so that we can give an expression for the internal loads at any point, or at every point. Okay, so those are the two things we still have to do with internal loads, and we'll see that dealing with the first one isn't very hard. We just have to introduce a new sign convention, and then it's one more thing you have to get used to. Sort of a nuisance, but it's not conceptually hard. The second one is where pretty much all of the trickiness of calculating internal loads comes from. It's not tricky to figure out how to calculate the internal loads at a point. It's tricky to figure out how to express those loads as a function so that we have a single expression that tells us what's happening throughout the whole beam. Okay, so let's take a 10-minute break, and I'll start again at 2:08. All right, anybody have any questions about what we just talked about? So here's the new sign convention. The first one of these is easy. The second one is harder. I mean, that's what most of the difficulty is going to come from. But to deal with the dependence on the calculation approach, we're just going to introduce this sign convention. If you're going from this side, these loads are represented by a horizontal force, plane T, a downward vertical force, V. Like, okay, why is the T in the positive X direction? Why is the V in the negative Y direction? That's stupid, but we don't get to decide because someone decided this stuff long before we were alive. That's all. That's just how it is.
Is that a tension T or is that a...
That's a tension T.
Okay.
Then this V is the shear force. I'll write these names down. Then there's a moment about the Z-axis, M. And then there's a torque about the X-axis, fancy T. And if you're working from the other side, the tension is this way. All of these are equal and opposite. So tension is this way. Shear force is up. Bending moment is this way. And the torque is to the left. So T is tension. If you get a negative value of tension, that means the body's in compression. V is called the shear force. I don't know where the naming comes from. I don't know what that V signifies, but M is called the bending moment. And fancy T is called the torque, or the torsion. And using this sign convention, I mean, you can see that it just, that this is designed to get rid of that equal and opposite thing you get depending on which direction you work. So whichever one of these sets you use, you'd get the same number to represent the same internal load.
Bending or pending?
Bending. And for T, V, and fancy T, you're on your own for remembering the sign convention. But for the bending moment, remember that a positive bending moment does this. And a negative bending moment does this. Okay. So let's do that calculation again and see how it works with these new sign conventions. So I'm going to repeat the last example with new sign convention. Okay, so I'm going to skip the part of calculating the external loads again. Those would be just the same. And I'm going to isolate the left half again. So our external loads are positive 707.1, positive 707.1. That's a force. Then we have a couple of (5,000 Newton meters that way, and a bending moment of 707.1 that way. And then we have our internal loads. And our internal loads are a T to the right, a V down, M about the Z-axis, and then fancy T to the right. So Newton's second law says 707.1, 707.1 plus. So now the only other two forces are the T and the V. And this can be really confusing now because we're going from this new sign convention to standard coordinate axes in order to represent these as vectors. I think the easiest way to think about this is think about the arrow as indicating a unit vector. And you're just multiplying this scalar, T or V, times the unit vector in the arrow's direction. So the plane T is associated with an arrow in the positive x direction. Okay? So a unit vector in the positive x direction is 1, 0. Multiply T times 1, 0, and you get a vector T0. Okay? This V, that arrow is in the negative y direction. So a unit vector in the negative y direction is 0, negative 1. Multiply that by the value V, and that says that this vector is represented by 0, negative V. Okay? So Newton's second law says 707.1, 707.1 plus T0 plus 0, negative V is equal to 0, 0. And you get that T is equal to negative 707.1 newtons, and V is equal to positive 707.1 newtons. What does it tell us that T is negative? Well, that's true too, but it tells us that the member's in compression. Okay. So this negative sign means it's compression. And now rotational Newton's second law about the z-axis. For these internal load calculations, we're just always going to put the about point at the left end point. So we have plus 707.1 plus m does that force T produce a moment around that red point? No, because the line of action goes through it. How about V? V does. Its moment arm is 0.5. And would that force make it rotate clockwise or counterclockwise around the red point?
Clockwise.
Clockwise, so this is negative. So M is equal to negative 707.1 plus 0.5 V, and we can substitute in the value for V. And so we get that M is equal to negative 353.5 Newton meters. And then the last one is that internal torque. That's the moment equation about the x-axis. So we have negative 5,000 plus fancy T is equal to 0. So fancy T is equal to 5,000 Newton meters. Any questions about that?
Yes. I know we get Newton meters on the on our moment up above, but the 707 is in newtons. The negative 707 is in Newton meters, and why do we know this?
Okay, because we calculated, when we did the external loads, we knew all that stuff.
There we go. Okay. Playing catch up in my head here.
Yeah. Okay, so now let's do something similar, but this time instead of calculating the internal loads half a meter from the endpoint, let's calculate the internal loads x meters from the endpoint. Okay. From the left end. Okay, so I'm going to draw a free body diagram. But the free body diagram I'm drawing represents a whole family of x values, not just a single location on this beam. So we have this force of 707.1, 707.1. We have a torque of 5,000 to the left. We have a couple of positive 707.1 on the left. We have this stuff that we're not considering. And then we have the internal loads, T, V, M, and fancy T. And now this distance, it all looks just the same, except that now we don't know that this distance is 0.5. This distance is just represented by the variable x. Okay, so Newton's second law. Newton's second law is going to be just the same. I think one of the moment equations is going to be just the same, but one thing is going to end up being dependent on what x is. And what this is doing is getting us a step closer to representing these internal loads as functions of x that represent the whole beam instead of just representing a single point. So Newton's second law says 707.1 plus T0 plus 0 negative V is equal to zeros. So what this says is for all of the x values represented here, the tension is just equal to negative 707.1. It doesn't change. We still have to consider what x values this is valid for, but whatever x values it's valid for, we know that the internal tension is negative 707.1. And the internal shear force is positive 707.1. So now we'll go to the moment equation about the z-axis with the about point at the left end. So we have the couple of 707.1, the bending moment m, and then what's the moment arm for this force V? X. And that would produce a clockwise rotation, so this is minus Vx is equal to 0. And so m is equal to negative 707.1 plus Vx. And so m is equal to negative 707.1 plus 707.1x. And then the moment equation about the x-axis, we just have the negative 5,000 and the fancy t. So we get the same thing we did before, that the internal tension is equal to positive 5,000 Newton meters. Okay, so what we get is that for whatever interval of the beam where x is valid, wherever this treatment is valid, we'll think about that next. T, V, and the internal torque are constant. But the bending moment, in this case, and there's nothing really special about the bending moment. We can come up with problems where they all change, but in this case, the bending moment varies from point to point. According to that function that we found. Any questions about that? Okay, so in general, T is a function of x. V is a function of x. M is a function of x. And fancy T is a function of x. My kids have just been watching Simpsons every morning now. It's like I've never been more proud as a grown-up. Okay, so in general, these functions are piecewise functions. So the piecewise functions are like, you know, remember stuff like this. F of x is equal to 2x for x less than 5, x squared for x greater than or equal to 5. Those are piecewise functions, and that's the kind of thing that these are, generally speaking. And the individual functions that make up these piecewise functions are called subfunctions. And so we need to know where the subfunctions change that represent each of these things. And those subfunctions change, or can change, at the following places. Endpoints of the beam, places where point forces are applied to the beam, the locations of point couples applied to the beam, and the last one is locations where distributed load functions change. We haven't talked about what distributed loads are yet, but we'll do that. So locations where distributed load functions change. If there are n, capital N, points on the beam, that are in this list of 4 things, that have these features, you know what I mean? That's a stupid way to say it. Dang it. Then these piecewise functions are going to be represented by n-1 subfunctions. Or in other words, we're going to have to do n-1 of these cuts where we isolate a piece and represent the end in terms of x. So we'll represent T, V, M, and fancy T using n-1 subfunctions. Any questions yet? Okay, so one thing to notice is this is going to be a confusing thing, and then it'll stop being confusing, and then sometime at 11:30 at night or something, it's going to get confusing again out of the blue. You know what I mean? That's just how it has to be. But notice that the isolated body always includes the whole beam from the left endpoint, from the left end of the beam to X on the right. So there's going to be, so for example, if you have a beam like this, say there's a force there, a force there, and a force there, okay? Your first cut is going to look like this. Okay, and it's going to be valid for all x values between the left endpoint and before you get to that midpoint. The second cut is going to represent all x values between the midpoint and the right endpoint. Okay, so if this distance is like, say this is 0.5 and this is 0.5, cut 1 is valid for any x between 0 and 0.5, not including those two endpoints. Okay, so the x values we get from isolating this first piece are going to represent any x value between 0 and 0.5. This second cut is going to be valid for any x's between 0.5 and 1. Okay? And here's the thing that's going to be confusing at some point when it's the least convenient possible, is you're going to look at this and say, wait a second, why are we isolating, why is this cut going all the way to the end, to x equals 0, if this is only valid for 0.5 to 1? You know what I mean? Anyone know what I mean? No? Okay, I don't care. That's because this range is only talking about where the right end is. That x value only represents where the right end is. You're isolating the whole thing, okay? You're going all the way from the left end to an x value that's within this range. If you didn't do that, so why would you not, why would you do it that way? Because if you think of what a pain it would be if you isolated a piece that went to some intermediate place on the beam. Not only would you have to deal with the internal loads on this side that you're trying to calculate, but you'd have to deal with internal loads applied to what you're isolating by the stuff on the other side. It would just be unnecessarily complicated. So we'll go all the way from the left where we know all the external loads, and then the only stuff we have to calculate is here. Okay, let me do an easy example, quick example. So let's say that we have a beam that's connected to a pin joint at the left and makes contact with the ground through a roller at the middle. And let's say that there is a 1,000 Newton force there and a torque T at the end point. And these distances, let's say a meter between those two and a meter between those two. And we want to calculate the internal loads. Well, first we have to calculate the external loads, so we'll isolate the whole thing. You have a force vector here, I'll call that RA, and that's a force vector because this is a pin joint. And then you have a force with a known direction from the roller that's acting straight up, I'll call that RB. And then at the right end you have 1,000 and T. Oh, and I missed one thing about this. The pin joint at the end keeps this thing from, so if you're applying a torque about the axis, that pin joint keeps it from rotating. So I'm going to also put a reaction torque, I'll call it TA at the end. Okay, so Newton's second law says RA, I'll break it into components, plus 0, negative 1,000 is equal to zeros. So that vector RA is equal to 0, positive 1,000. Oh no, whoops, I missed a force. I missed the 0, positive RB. And that's equal to zeros. So RAX is equal to 0. RAY is equal to 1,000 minus RB. Then the moment equation about the z-axis. I'll do my about point at the left. There's no moment produced by RA for this about point. RB has a moment arm of 1. And is that clockwise or counterclockwise? Counter, so that's positive. And then the 1,000 has a moment arm of 2. Is that clockwise or counterclockwise? Clockwise, so that's negative. And that's equal to 0. So you get that RB is equal to 2,000. And plug 2,000 in for RB up above, and you get that RA is equal to 0x negative 1,000y. And then the moment equation about the x-axis says TA where's the problem? This doesn't make any sense. I have to give you a number here. So go back to the example up here where I wrote T here. I'm not sure what was going through my head there, but that needs to be, let's make that 500. Okay, so TA plus 500 is equal to 0. And so TA is equal to negative 500. Yep. In the original, when I originally defined this problem, I think I was writing while I was thinking about something else. This is supposed to be an external load, and I had to give it a number. Okay. Any questions about that? So we didn't get to the internal loads. Let's just stop there, and I'll use this to do the internal loads on Monday.